In our previous video, we used the constant acceleration of g equals minus 10 meters per second squared to update our y velocity each second, which gave us this changing vector, becoming less steep each second, but still traveling the same distance horizontally since we have no horizontal force on this motion. And then we used the velocity at the beginning of each second to project the position forward for that second's motion. In this video, we're going to take this same method and apply it in a spreadsheet so that we can make it more automatic. And if we wanted to update it twice as often, say every half second or even every tenth of a second, we can do that automatically with the spreadsheet. So let's see how that works. So here we are in sheets.google.com. I'm going to open a new blank spreadsheet and I will save this as tile motion 1. In this simulation, I'm going to use each column to record data over the progress of time, and the first column will be time itself, measured in seconds. The second column will be the x velocity, measured in meters per second. The third column will be the y velocity, measured in meters per second. The fourth column will be the position in x, measured in meters. And the fifth column will be the position in y, measured in meters. To the right here, we'll record some important constants for the simulation that will let us change parameters automatically later when we want to investigate different initial conditions. Let's begin with the time step. I'll call it dt, short for delta t. We'll start with this as 1 second, just like in our graph paper simulation. We'll call our initial velocity v0, and I will make that 50 meters per second. Our initial launch angle will be called theta, and we will make that 53 degrees. Now we'll use these parameters to simulate the motion over time. Let's begin with time. My initial time will be 0, and now I'm going to use a formula. I'll type equals, click on the cell above, which says, let this cell be equal to the cell above it plus a certain amount. That amount is the value contained in dt, and here I want an absolute reference. As I move down this column, I don't want to move down column G with values of dt. I want to keep this value in column G, row 2, so I'm going to use a $sign to lock the column and row for that value. Here I've added 1, we progress forward, and we have seconds 0 to 9 automatically promoted. We remember that Vx is our initial speed, which is located in h2, and again we want to lock that value, $h, $2, times the cosine is what gives us the horizontal component, and cosine automatically expects radians, which is a different angle measure from degrees. So I'm going to use this function to convert radians of $i, $2, and this will give me my horizontal velocity in meters per second. Let's reduce the number of decimal places on this column to make it look a little bit simpler, 30 meters per second, which you might remember from the previous video. Now we remember that the x velocity doesn't change over time. The y velocity, however, will change over time. Let's see how we implement that. I'm going to use equal, which I always need to do for my velocity as a function of time. It will equal my initial velocity, again locked with $signs, $h, $2, times the sine of the angle, which we remember we need to use the radians function to convert from degrees to radians, and that is in I2. Again, we click here to reduce our number of decimal places, and now we need a value for gravity. I will call it -10 meters per second squared. The y velocity is going to change, so each new value will equal the value above it minus this value of g, which is what? $j, $2, times how much time has gone by, which is in G2. And again, we want to lock that with an absolute reference using the $signs. And we want to get our sign correct. I'm using -10 to mean the acceleration is downward, and I'm adding that amount. Adding a negative value decreases the overall y velocity, and we know as an object moves up, it's going to lose vertical speed, losing vertical velocity because gravity acts downward. Here we've been decreasing the velocity over time, which we know is what happens. Our x position initially is 0, and we're going to advance from whatever location we have by an amount that's equal to the x velocity at that time times how much time has gone by, which is g2. We're locking that g2 with dollar signs. And we're not multiplying, but adding. Again, for this column, I highlight the whole column by clicking in the uppercase D at the top, and I've reduced the number of decimal places. Adding this, we should be counting by 30s. Let's check. Looks good. Now for y, we begin at 0. The height at the beginning of the launch, we'll assume we're launching from ground level. And the next position is going to equal the previous height plus the velocity at the beginning of the previous second times how much time goes by. For this whole column, again, we're using just 2 digits, and projecting that forward, we have this pattern which I see is increasing up to 100. I remember that from the graph paper, and then decreasing back down. I see it's not exactly 0 here, but close. Now let's check and compare our graphs of Vx and Vy as a function of time. I'm going to use Insert Chart after selecting columns A, B, and C. I want not a column chart, but a scatter plot. My x-axis here is time, which I check in the setup for the chart, and I see that I have a constant Vx of 30 and a decreasing Vy with a slope of -10, progressing from positive to 40 to -40, a change of -80 over 8 seconds, which is a slope of -10. This looks good to me. Next, we'd like to graph x. Y is a function of x. We're highlighting columns D and E. Click Insert Chart. Again, we want a scatter chart. This is the expected parabolic behavior. I want to adjust my vertical axis. I'm going to make the minimum 0. And let's make the maximum a little bit higher so we can see detail at the top. 120 over here in the Customize menu. If we click on Series, we can also add a trend line. I know from previous discussion that this is going to be a polynomial of degree 2, and I can label it with the equation. This gives me an equation for y as a function of x in meters. Now, because of the way I use those dollar signs, I can reduce the launch speed from 30 to, say, 25. I notice I launched to about 271 meters. Let's adjust the initial speed to half that value. And now I can see the particle is landing at 75 meters. Returning back to initial speed of 50, I can also adjust the launch angle. Instead of 53, let's try 45. Here we can see the particle has gone further at 45 degrees than it did at 53. More horizontal velocity, but less vertical velocity, and we've got more range out of it. We can repeat with a launch angle of 37 degrees, and I notice something interesting. I have about the same range for 37 degrees that I had for 53 degrees. 280 versus 271. There's a lot of approximation in this technique that we're only updating every half second. Can we make this more precise by changing our time step? Let's make our time step half a second. We'll change delta t to 0.5. And now I notice I don't have the full flight path, but we can recoup it by, remember, click in the lower right of a cell when I get this box and cross, click and drag down, and it will apply that formula further. Now we have the full flight path again, and it's updated our prediction. I can see I have a range of 256 meters for a theta of 53, and a range of 260 meters, much closer to each other, for a range of 37. Remember, 37 and 53 add up to 90. We can make these data points twice as often, every quarter second, and again increase our number of points in the simulation. Let's adjust our y-axis. Take a look at the spacing here. When is the particle moving fastest and when is it moving slowest? When these dots are closer together at the top, those are equally spaced in time, but they're much closer to each other. What does that tell us about the speed? When we come back down, we get the same speed we had to start as the particle accelerates towards the ground. So that's an overview of how to use Google Sheets to simulate the motion of the particle. Y is a function of x. Notice we can also have y as a function of time. I can click in column E, column A, insert chart. Let's customize and change our vertical axis, make the minimum 0. So we don't have this data that came below ground. We know that can't happen. And here we have a second parabola. Let's also click on series and add a trend line. I would like polynomial of degree 2, and let's label it with the equation. So you may remember from our tale of two parabolas that we had two different equations. One of them is y as a function of x here in the upper graph, and the other is y as a function of time.